talking about क्या बात है मुझे याद ही नहीं. We were talking about moment of inertia. होमवर्क में क्वेश्चन दिया था. क्या क्वेश्चन दिया था? Nine squares वाला. I think only one person gave me the answer, and I think that was the correct answer. So this is basically you have to understand I'll give you a hint, then try to solve. अभी रुक जाओ अभी. I'll just shift to somewhere else. Construction work. So we know that moment of inertia is mass into distance square, right? And we also know that if this side is L, let's say, and this side is L. Now, supposing if I were to consider an object which is 3 times the size. Supposing that I were to consider an object which is 3 times the size. Now, if the moment of inertia of the original object is I, okay, which we have to find out. Can you see that why have I increased it by a factor of 3? Because if I increase by a factor of 3, what happens? If I increase the size of the original object by a factor of 3, what happens? If I increase the size of the object, हाँ, इसका मतलब क्या हुआ निश? What does this mean? If I increase the size of the object by a factor of 3, moment of inertia increases, yes, Pratiksha, but why did I choose 3? I could have chosen other numbers as well, but the thing in choosing 3 is that one of these squares, in fact, all of these squares really, this is the original object. This is the original object. Yes, exactly. So what is the moment of inertia of this new object? Moment of inertia of this new object will be how much? Moment of inertia of this new object will be how much? Well, I know that moment of inertia is mass into distance square. So by what factor has the mass of this object increased? By what factor has the mass of this object increased? It has increased by a factor of 8. बीच में कुछ नहीं है ना? How many original objects are there here? There are 8 original objects. Right? Am I correct? Is everybody understanding? There are 8 original objects.
सर आप original object को छोड़ के बोल रहे हो बाकी?
नहीं, original object छोड़ के थोड़ी ना मैं बोल रहा हूँ मैंने original object को factor of 3 से बड़ा कर दिया तो उसका mass कितने से बढ़ गया? अगर मैंने original object के sides को factor of 3 से increase कर दिया and I get this, then the mass has been increased by what factor? Is it 3? Is it something else? Has to be how much? Has to be 8 multiplied by 3 square into I. 3 square कहाँ से आया? 3 कहाँ से आया? आओ भाई जल्दी जल्दी, 3 कहाँ से आया?
सर लेंथ जो है वो 3 से बड़ी है और ब्रेथ भी 3 से बड़ी है, मतलब डिस्टेंस स्क्वायर है तो वो बाहर आ जाएगा फिर।
Exactly. So this means that the moment of inertia of the new object is 72 times the moment of inertia of the original object. The moment of inertia of the new object is 72 times the moment of inertia of the old object. Okay? Of the original object. Now, can you use a combination of parallel and perpendicular axis? Well, you don't need really perpendicular axis. Only parallel axis. For this thing about this axis, you already know that the moment of inertia is I. 3 square, distance square beta. Yeah, distance square. Moment of inertia is mass into distance square. So if I increase the side by 3, then I'm basically increasing the distances of all the objects by a factor of 3. Okay. अभी बताता हूँ खुशी अभी हाँ खुशी is asking why have I increased by factor of 3. Kushi, are you asking why have I increased it at all, or why only the factor of 3?
Sir, why you have increased at all?
Very good question. सबको पूछना चाहिए भाई. Can anybody answer why have I increased it? Can anybody answer why have I increased it? Okay, I will answer. So if I increase the size of the object, okay, I can additionally decrease also. If I increase the size of the object, then we have, you will agree, right, Kushi, that we have this guy, we have this guy, we have this guy. These are all original objects. Inka moment of inertia mere ko nikalna hai. I have to figure out the moment of inertia of these. Now the moment of inertia of these guys, let's say is I, and if I can figure out the moment of inertia of the big object in terms of I, which I have done, then all I have to do is use parallel axis theorem to find the moment of inertia of this big object in terms of I and put it here. So I should get an equation in terms of, I should get a single equation with only one variable, that is I, which should give me the value of the moment of inertia. आया समझ में यार? खुशी? Okay, let me think of an analogy. In physics, this is actually quite common. And in physics, this is called the scaling argument. What is the scaling argument? The scaling argument is that if I have an object, and if I can scale this object, a larger one, or vice versa, scale this object to a smaller one, then if I know the properties of this larger guy, I can work my way backwards to work out the properties of the smaller guy. Yeah. Or if I know the properties of the smaller guy, then I can work my way forwards to work out the properties of this guy. an example. I don't know if this is a valid example or not, but it is a very interesting example. Can we predict the size of the biggest animal that can be there on Earth? Now, I know that we have all seen movies, Godzilla and King Kong and I don't know, Pacific Rim. So in all these movies, they show huge monsters. स्काई स्क्रेपर के साइज के चल रहे हैं रोड पे, तो सारा स्काई स्क्रेपर ही उड़ जा रहा है, गिर जा रहा है. So is it possible to have such monsters? Is it possible to have such huge sized animals in reality on Earth? So you may say that, look, it is not possible to find out because the dinosaurs, they died a long time ago, and we do keep on finding fossils, and every 5 years or 10 years or so we find a fossil which is greater than the previous greatest found fossil. How can you predict? But with the scaling argument, it is actually easy to predict. So what you can do is you can take the human leg bone or any other animal's leg bone. I believe it is called tibia bolte, if I remember correctly my biology. So if you take the human leg bone, that is the bone which is connecting your knees to your feet, or you can take the thigh bone, it does not matter, and you measure the average weight of a human, the size of the human, and the radius of the bone, right? That will give you a rough estimate as to the ratio of the size with respect to the radius of the bone. So if you scale forwards, if you say that, look, I know that a human exists, or I know that an elephant exists, right? And this is by the way, this is all of this is very, very scientific and proven. So if you take an elephant bone, if you take a human bone, human weight and elephant weight, and if you calculate the ratio, then that ratio comes out to be roughly equal, right? Ratio of weight to the radius of the bone. So you can scale it forward and you can ask whether something having a weight of 1,000 tons can exist or not. And when you scale it, you find that the radius of the bone comes out to be, very preposterously high. So it may come out to be something like 50 meters. Now we know that nothing can exist which can have a sort of bone radius of 50 meters. That will not be possible, because if you do have a bone radius of 50 meters, then the bone itself will have weight, then you need muscles to lift that weight, and so on and so on. So using this scaling argument, we can predict the largest animal that that has the possibility to ever exist on this planet. Right? So in the same way, what I am doing is, I am making this object bigger. Right? I am making this object bigger. Right? Now, why can I do that? What is the thought process, or what is the logic behind when can I do that? Can I only do that with human bones and elephant bones and elephant weight? Can I do it with everything? Well, we can do it where the structure of the object remains constant as I scale it up, Okay. So human, elephant, nice, small, nice. नहीं Pratiksha, उसपे क्या है ना ये, so the question is now, can we then predict the smallest? No, we cannot. No, we cannot. We can predict the largest, but we cannot predict the smallest. Because when we go to the smallest, then you find that let's say that we are talking about an insect. Then the insect does not have a bone. So the thing that the bone we are scaling on the basis of the size of the animal, size of the bone, and the weight of the animal. But if something is like an insect is having no bone whatsoever, then you cannot extrapolate it to that. Okay? So there are limitations to this scaling argument, obviously. So we want to scale an object which maintains some sort of a structural similarity as it either scales up or it scales down. Okay? So in this case, if I scale this object up, it will essentially be the same object, because this will also be a square in which the thing has been divided into 9 equal parts and the middle part has been taken out, and so on and so on, right? So that is why I have scaled the object to a larger one. I could have gone L by 3 as well. Uska bhi structure same rehta hai. I could have done that as well. But I decided to scale upwards because I don't know, because I would be working with the original moment of inertia. If I decided to scale backwards, तो I dash जो है वो यहाँ रहता, I जो है वो यहाँ रहता, और ये I by 72 हो जाता. I dash is equal to I by 72. That would also have given us the answer. That would also give us the answer. So I've scaled it up because using this relation, I can find the relationship between the moment of inertia of the original object and the scaled object. I have scaled it because using this relation, I can find the relation between the moment of inertia of the scaled object and the original object. And after I find this relation between the two, using this, I can find another relation between the two moment of inertia using parallel axis. So essentially, while scaling, I know that I can use two things to find the relationship between two variables, and this would give me two equations of two unknowns which I will solve.
सर हमारा जो रेफरेंस वाला एक्सेस है वो तो बीच में से पास कर रहा है ना, जहाँ कुछ भी नहीं है उसके बीच में.
बिल्कुल.
तो फिर हमने ये क्यों लिया, मतलब फिर तो डिस्टेंस हर एक ब्लॉक के सेंटर ऑफ मास का अलग अलग है ना, 3 थोड़ी है.
हाँ, वही 8 बार कैलकुलेट करना पड़ेगा. 8 बार करना पड़ेगा, बट आई कैन डू इट. वही मैं करने जा रहा हूँ.
सर 2 बार ही करना पड़ेगा.
हाँ, एक्चुअली 2 बार करना पड़ेगा.
नहीं सर, मैं आपके ऊपर वाले एक्सप्रेशन में पूछ रही हूँ जहाँ आपने 3 स्क्वायर लिया, वो अभी भी नहीं समझ रहा क्यों लिया.
ये 3 स्क्वायर नहीं समझ रहा. ओके, ये मेरा ओरिजिनल ऑब्जेक्ट है और ये एक्सेस ऑफ रोटेशन, ठीक है ना.
यस सर.
अब ये जो ओरिजिनल ऑब्जेक्ट है, इट इज, लेट मी जस्ट draw the dotted line. Now, how will you find moment of inertia of this object in the most crude manner, in the most raw manner? How will we find the moment of inertia? We will say that, look, this is a particle, right? Center पे हो सकता है particle ना हो. By the way, I'm just arbitrary. मैंने यहाँ पे I'm assuming कि यहाँ पे mass है, तो उसमें से एक arbitrary mass मैंने choose कर लिया. और मैं ये डिस्टेंस निकालूंगा और मैं उसको मास से ये डिस्टेंस स्क्वायर करके मल्टीप्लाई कर दूंगा। इसी तरीके से यहाँ पे मास है, यहाँ पे मास है, यहाँ पे मास है, यहाँ पे मास है, यहाँ है, यहाँ है, Now, if I scale this object up 3 times, if I scale this object 3 times, okay, again I draw the 9 squares. Then, if I take the same particle,
Yes sir, समझ गए अभी.
then by what factor has this distance increased? मेरा diagram थोड़ा गड़बड़ है, but the factor with which the distance has increased will be
Same as the scaling factor.
on an average, we can say that all distances will increase by this. So, I plus how much? M into how much? ये डिस्टेंस कितना होएगा? इसके सेंटर से छोटे स्क्वायर के सेंटर से बड़े स्क्वायर के सेंटर तक कितना होएगा भाई बताओ? Somebody? क्या हो गया भाई? इतना टफ क्वेश्चन थोड़ा ना पूछ लिया. हाँ, फिर से बोलो. नहीं समझा. √12 होएगा.
√12, yes.
And I can do this into 4 because there is 1, 2, 3, 4 plus I plus, now I'm moving from here to here. ये कितना डिस्टेंस होगा? ये कितना डिस्टेंस होगा? L होएगा ना मेरे ख्याल से.
Yes sir.
L square whole into 4. 1, 2, 3, 4. So I get 8I plus 8 ml square plus 4. 12 ml square is equal to 72I. So this tells me that 72 minus 8 is 64I is equal to 12 ml square. So I is equal to 12 ml square by 64. That is equal to how much? 3 by 16 आएगा मेरे ख्याल से. 3 by 16. नहीं.
3 by 16.
3 by 16
3 by
आएगा ना?
16.
sir, 3
Yes
by
sir. 3 by
16
16 होगा.
3 by 16. This will be
सर इसी क्वेश्चन को जीपी से करने का कोई तरीका नहीं है?
ये क्या हुआ भाई? फिर से मेरा गड़बड़ हो रहा है कुछ. ओके, ठीक है. So
सर इस
this
क्वेश्चन
is
को हम जीपी
all
से कर
about.
सकते हैं क्या?
हाँ,
क्वेश्चन को हम जीपी से कर सकते हैं क्या?
जीपी से करना चाह रहा है, जीपी से कैसे करेंगे?
सर हमको लेंथ पता है कि 1/3 ऐसे मतलब होती जा रही है, तो हम लोग इन्फिनिट सम लगा लेंगे हर एक आई निकाल के।
हर एक का जो आई निकलेगा वो तो कैसे करेंगे?
लेकिन
एक
हर
बार
एक
करके
का
मेरे
आई
को भेज
उसके
अगर,
एक्सेस के अबाउट ही होगा ना।
हाँ वही वही प्रॉब्लम है ना,
हाँ सर।
वही प्रॉब्लम है। चलो okay, so this was all about moment of inertia. Okay, now we move on to the rotational counterpart of force, that is torque. So torque is a vector quantity. The symbol of torque is the Greek letter tau. The units of torque are Newton meter, which is the same as the units of work. However, they are completely different physical objects, right? So two objects can have the same units but be completely different. There is no problem in that. The mathematical definition of torque, is that torque is equal to R cross F. Right now, we will take some time to discuss this. So at some point of time, I think it was found that Newton's laws are F is equal to ma, or the laws containing F is equal to ma are quite insufficient to describe the motion of rigid bodies. And this is very obvious. You have experienced it. You can experience it right now. If you try to open the door of your room, right, so there is a handle. You use the handle to open the door of your room. Now, what would happen if the position of the handle is moved towards the hinge? So, physically, तो हम obviously door के handle को अभी उठा के hinge की तरफ नहीं कर सकते. लेकिन अगर आपका door थोड़ा सा खुला हुआ है, तो what you can do is you can reach up to the top and you can put your finger on the top of the door and try to pull it, try to open the door, and you will see that to maintain the same acceleration, you have to apply more and more force, right? Absolutely right now. Force ज़्यादा लगानी पड़ेगी. As you keep on moving towards the hinge, you have to apply more and more force. And when you are at the hinge, when you apply a force on the door, but you are applying a force on the door at a corner which is on the hinge, then you will find that no matter how much force you apply, the door will not open. So it turns out that for rigid bodies, not only does the magnitude and direction of the force matter, the position of the force applied on the rigid body also matters. So if I have applied a force on a rigid body, or if I have applied two forces on a rigid body, having the same magnitude and same direction, but having different positions on the rigid body, then the effect of these two forces will be completely different. Right now, I am talking about the door. So you can always say कि नहीं नहीं उसमें तो hinge लगा हुआ है, because we can take a rigid body like your pen. You can keep your pen on the table, flat, horizontal, and you can apply a force, the same force, same direction, same magnitude at different positions of the pen, and you will see that the pen is responding in a different manner every time. So that Newton's law will need an upgrade that to describe the motion of the rigid body. It is not only force. आवाज नहीं आ रही है? रुको. Wait.
सर अब आ रही है,
Wait.
पहले चली गई थी
रुको.
सर।
ये पीछे भड़बड़ की आवाज तो नहीं आ रही है? बहुत ज्यादा है कंस्ट्रक्शन में आवाज
आ रही है।
सर आ रही है।
अच्छा रुको, I'll just shift to somewhere else. So at the application of force, so the force itself is not enough. You need to know the point of application of force, right? That also becomes important. But how do we incorporate the point of application into our calculation, right? That's a very weird thing. Point of application. We do not know what the rigid body is going to be, right? So we do not know. We do not know with respect to where should I measure the point of application. Nevertheless, point of application must be in our calculation, must be there because it is invariably affecting what is going to happen. So therefore, we define this new quantity called torque, and this is really the first instance where cross products they come into play. Actually, cross products did come into play in circular motion as well, but as you will see here, it is very difficult to analyze circular motion or rotation in more than 2 dimensions, right? So we generally avoid it. We reduce it to one-dimensional. Therefore, we can label the sign of angular or rotational variables as plus or a minus. So omega is not r omega. It is, sorry, v is not equal to r omega. It is actually equal to r cross omega. I think it's r cross omega or omega cross r. मैं भी भूल जाता हूँ because we don't use it. Acceleration is omega cross r. So we don't use that because generally we are not going to deal with 2-dimensional or 3-dimensional rotation. Here also, although I have written a cross product, I will tell you a method to find torque which does not require any cross products, assuming of course that all the torques are along one axis, as they are going to be for all the problems that we are going to discuss. At the very end of this chapter, we will come back and we will discuss 3-dimensional, 2-dimensional, 3-dimensional rotation. Okay, but up till that time, we will assume that everything is happening in one plane. So, what is R? What is R? Well, it turns out that this R is the position vector point of application of force. Immediately you should ask me what? Immediately you should ask me what?
With respect to what point?
With respect to what? With respect to what? Because position vector is a vector drawn from the origin to the point or to the location, in this case, of the point of application of the force. Right. So it is with respect to any This is very weird. This is extremely weird. So basically, I'm telling you that look, anybody can measure a different value of torque, and this is actually the first step that you are taking in real life physics, where these things are actually very common. That everything is with respect to the observer, and different observers have different perspectives. Especially when we go into magnetism and magnetic force, you will see that everything is with respect to the observer, right? In fact, this is why Einstein's statement was path-breaking, the theory of relativity. He says that the speed of light is constant with respect to any observer. That is a very path-breaking statement. So yes, absolutely right. The torque is such a quantity which is dependent on the observer, which is dependent on the choice of origin of the observer. So if only one force is producing torque, then it is absolutely possible that one observer will be there who will say कि नहीं torque to zero लगा. अगर केवल एक force लगी हुई है, तो then it is absolutely possible for one observer to be there who will say that the torque is zero, because that guy will place the origin at the point of application of the force. And if you place your origin at the point of application of the force, then the position vector of the point of application of the force will have a value of zero, and therefore the torque will be zero. So different observers will measure different torque. Will the different torque measured by different observers be the same in direction and different in magnitude, or can it have a completely different direction as well? The answer to that is yes, it can have a different direction as well, right? So the torque vector will be something which will be measured differently by different observers, right? And we have to reconcile with this. When we are doing a problem, when we are solving a problem. Now we have an additional burden, although it will not be a burden for us, because for us the choice of origin will be very strict. The choice of origin will be very limited for us. But in theory, you can have infinite number of choices of origin, and for each origin you may get a completely different value of torque. Now you are going to use this cross product only in one scenario. You are going to use this formula of this cross product formula of torque only in one scenario. Right? So you will use this when R is equal to something I cap plus something J cap plus something K cap is given, and F is something I cap plus something J cap plus something K cap is given. In fact, I will give you an example. Find torque if R is equal to minus I cap plus 2j cap minus 4k cap f is equal to 3i cap minus 6j cap plus 8k.
सर वो 8 के कैप है।
नहीं, मैंने गलत लिख दिया। 12 याद है किसी को क्रॉस प्रोडक्ट कैसे निकालते थे? है
सर 0 आ रहा है क्या सब में?
क्यों ये?
हाँ सर।
नहीं, 0 कैसे आया?
सर पहले बीच वाले में बनाया, देन 2 2 into 12 minus 4 into -6 ऐसे क्यों?
पहले वाले रो में क्या लिखे?
सर पहले जे में बना, पहले वो डिटर्मिनेंट बनाया एंड देन उसमें बीच वाले में सबसे पहले वो किया, नहीं मतलब फर्स्ट वाले में सबसे पहले किया, तो उसमें 12 into
क्या
2
तो ऊपर आ रहा है ना।
है?
सर आई जे के वाला हम लोग ने डिटर्मिनेंट बनाया एंड देन उसमें वैल्यूज भर दी हम लोग ने सारी नीचे, फिर उसमें आई वाले में हम लोग ने लाइन बनाई एंड जे एन के कंसिडर किया हम लोग ने, तो उसमें 2 into 12 minus -6 into -4, तो वो कट रहा है पूरा। सिमिलरली सबके लिए हो रहा है।
सबने यही किया, केवल तुलिका ने पकड़ा है क्या हुआ है? सबने यही किया, एवरीबॉडी हैज डन दिस। राइट दीक्षा, गलत आंसर। हाँ तो सही बात है ना तरुण, तो क्या हुआ?
सर आर और एफ परपेंडिकुलर है।
नहीं भाई,
सॉरी सर, पैरेलल पैरेलल पैरेलल।
मैंने बोला था कि मैं आप लोग को 3 बार बेवकूफ बनाऊंगा। जब मैंने आपको डिटरमिनेंट पढ़ाया था, I gave you parallel vectors and every time you use the determinant to find the answer to be 0. And I said that I will make you do this 3 more times at least. And I told you to remember, whenever a cross product is, yes man, yes. Whenever a cross product is carried out between 2 parallel vectors, the cross product must be 0. And these are 2 parallel vectors, right? If you look carefully, then r multiplied by -3 gives you f. You did not need to draw the determinant in any way. Chalo, now only 2 times remain. Yes, common factor ले लो, जो करना है कर लो. I mean, you just have to conclude that these two are parallel to each other. In this case, anti-parallel to each other, and therefore the cross product will be 0. मैं 2 बार और करूँगा during the course. Please remember this. Okay, whenever you get 2 vectors in an exam, first thing to check is parallel or anti-parallel. If they are, then the answer is 0. If they are asking you for the cross product. Second thing also, please remember, very important, remember that this is R cross F. Never write F cross R. Remember that cross products are non-commutative. They don't commute. You can't change the order of multiplication, right? So the R cross F, not F cross R. Okay. So with that now out of the way, and with the understanding that torque is something which is an additional thing required to analyze the motion of rigid bodies. As far as point particles are concerned, or collection of point particles is concerned, there is no problem. It is only when we come to deal with bodies which have dimensions, which have length, which have breadth, which have height, then these things come along. Okay? So keeping these two things in mind, number one, what I said, and number two, that we are going to deal with generally forces and R which lie in the same plane, so that our torques, which are cross products, which are perpendicular to both R and F, will be only along one axis, right? Preferably along the Z axis. When we studied rotation and when we studied about omega, we talked about clockwise rotation, anti-clockwise rotation. So I'm going to do something similar here. So finding torque mechanics. So we have a rigid body here. And on this rigid body, there are forces acting. So this is F1. This is F2. This is F3. So please notice that whenever I give you a rigid body and I tell you the forces that are acting on the rigid body, then not only must I tell you the magnitude and direction of all the forces, I must also tell you where these forces are acting on the rigid body. That is very, very important. If I drew all these arrows from a single point, then we could partially examine the motion of the particle. We could not fully examine the motion of the particle. So we are going to choose an origin here. And just write it. So step one is to draw the rotational free body diagram. But now we have drawn what we will call from now the translational free body diagram. Now, if you remember when we were drawing these free body diagrams in Newton's laws of motion, I insisted, in fact, if you ever noticed me drawing the free body diagram, I always drew all the forces from the center. Some of you have a habit of drawing the forces upar, niche, daye, baye, but I made it a point to draw all the forces from the center or from the origin. If I had drawn a coordinate axis there, irrespective of where these forces were acting on the object, because ultimately the object was a visualization of a point particle, right? We discussed this in the very first class. I told you that even if I talk about a car, or even if I talk about a block or a wedge, ये सारी चीजें जो हैं ये हमारे ideal world में, हमारे Aristotelian world में, they are point particles. But now we are not dealing with point particles anymore. We are dealing with objects which have shapes and sizes. So to draw the free body diagram here, which we will call the rotational free body diagram, there's only one difference really between the rotational and the translational free body diagram, and that is that in the rotational free body diagram, you draw the forces as and where they act. In the rotational free body diagram, you draw the forces as and where they act. So the rotational free body diagram implies that you draw the forces as and where they act on the rigid body. Okay, as I have done here on the left hand side. Step 2. So unlike what we did in translation, we don't have to draw an axis here. We don't have to take components. Okay? This is extremely good. I mean, I find it very, very satisfying that I don't have to find components of forces. So I don't have to find, you don't have to find components, you don't have to draw any axis, but you do have to choose an origin. Now the question arises कि आप ये origin कहाँ choose करोगे? Where will you choose this origin? So the rules are very simple actually. The rules are that the fixed point on the fixed body. So if you have a body which is fixed at a point, for example, the door was fixed at all points on one edge, on one side. If I were to take a nail and if I were to nail a disc on the wall, so जहाँ से मैं nail को drive करूँगा, that will become the origin. Another thing that I must at this moment warn you is that there is a slight difference between the origin and the axis. I think we had a very small discussion about it in the moment of inertia. So if I tell you that you have to find the torque about an axis, then that would have a different meaning as compared to finding the torque about an origin. In a very large number of cases, both the meanings will be similar. In a very, very large number of cases, both the meanings will be similar. But that does not mean that they are same. There are cases when the meanings of finding the torque about an axis and finding the torque about an origin is different. How is it different? Well, finding the torque about an origin means that you are finding the net torque about that origin. R cross F, you are applying R cross F one way or the other, you are applying R. Finding the torque about an axis means that you are finding only those components of torque which are parallel to the axis. You are not bothered with components of torque which are perpendicular to the axis. Right? Now, like I said, in most cases, these two things have the same meaning. Whatever problems we are going to do, in most cases, they will have the same meaning. However, there is an excellent article on this in HCV. If you read the rigid body dynamics or a chapter, there is an excellent article about torque about a point and torque about an axis. For the moment, for this moment, for the next few lectures, we will not make a distinction between these two things. So if I say choose an origin, this is just the same as saying choose an axis. Sometime later, I will tell you how to differentiate between the two. But for the moment, for us, it is the same. So choose an origin for a fixed body, for a fixed rigid body. It has to be that fixed point. And for a free rigid body, is the center of mass. Okay. For the moment, these choice of origins are, are recommended. You can choose other points as well, no problem. But that will complicate the calculations when you are doing the numericals. Okay, so here I choose this red point as the axis. In simple free body, I'm telling you that this is the center of mass. Now, अब हम ट्रांसलेशन से बिल्कुल ही अलग जाने वाले हैं. The next step is to extend these force vectors. You can do it mentally, you can do it in your mind, or you can do it on the paper. I prefer on the paper. So step 3, extend the force vectors. Step 4, drop perpendicular from origin onto extended force vectors. It's easy. Drop a perpendicular. I can't drop a perpendicular here because it is passing through the origin. Perpendicular, perpendicular. Step 5. If an extended force vector passes through the chosen origin, then the torque due to that force. See, right? So please remember, at the end of the day, it is only forces which are producing torques. Okay, and we know forces, right? We know forces can be generated by only 5 objects in the surrounding. That is string, earth, surface, and external agent. Of course, now when you study fluid dynamics, fluid mechanics, it will be fluids. When you study gravitation, it will be other masses. When you study electrostatics, it will be other charges. When you study magnetism, it will be other currents. So the mechanics part will remain the same, right? So whatever object is in the vicinity of your system will apply a force on your system, and this force will cause a torque if your system is an extended object, if your system has dimensions. However, an extended force, if it passes through the origin that you have chosen, then that force is incapable of providing a torque. Okay? The torque due to that force will be equal to 0. So let this be R1, let this be R3, let this be R4. Step 5. Step 6. The torque will be equal to F1R1 plus 0, F3R3, F4R4. So basically, the magnitude of torque, I'll write it here, magnitude of torque is equal to magnitude of force multiplied by the length of the perpendicular. Okay? The magnitude of force, magnitude of torque, sorry, is nothing but, as generated by a force, is nothing but magnitude of that force multiplied by this perpendicular, by the length of the perpendicular that you have dropped from your chosen origin onto that extended force vector. However, we need to, जैसा मैंने अभी नीचे लिखा है, मैंने उसमें प्लस माइनस नहीं लिखा, डायरेक्शन नहीं लिखा. We need
F3
to,
R3 माइनस आएगा ना,
हाँ
F3 R3 माइनस आएगा ना,
क्या बोल रहा है?
F3 R3 में माइनस आएगा.
हाँ वही देखना है. Let's see. हाँ, very good. Yes. So we want to talk about the direction of torque. Okay. Now, since both the vectors R and F, okay, जो मैंने R1 लिखा है वो R वेक्टर तो नहीं है, लेकिन अगर मैं R1 वेक्टर ड्रॉ करूंगा तो वो रेड डॉट से लेके और F1 के जो ये ब्लू एरो बनाई है उसके टेल तक जाएगा. और जो R3 मैंने बनाया है वो तो परपेंडिकुलर डिस्टेंस है, लेकिन अगर मैं R3 पोजीशन वेक्टर ड्रॉ करूंगा from my chosen origin, then it will be a vector drawn from the red dot to the tail of the F3 vector. Similarly, the vector drawn from the red dot to the tail of the F4 vector will be R. So you will notice that all forces and all position vectors, they lie in the XY plane. They lie in the plane of the device of this paper. Therefore, since we know that torque is the cross product of R and F, it is guaranteed that the torque is going to be along the z-axis. That means it is going to be perpendicular to both R and F. In fact, it is going to be perpendicular to the plane formed by R and F. And since for all the forces, the plane formed by R and F is the plane of the book itself, therefore the torque vector must be outside, either pointing outside or pointing inside the book, the plane of the book. How do we deal with this? How do we क्या करें इसका? I don't want to deal with cross products to be honest with you, and I don't think you want to deal with thumb rule. हाँ, thumb rule लगा सकते हैं. Thumb rule लगा सकते हैं बिल्कुल. लेकिन thumb rule लगाएंगे तो ultimately we are dealing with a cross product, and I don't want to do that. I don't feel comfortable while dealing with cross products, and unless my hand is forced, नहीं आपको तो cross product ही करना पड़ेगा. Unless my hand is forced, up till that time I will try to avoid dealing with cross products. And since I have said this before, since most of the problems that we will be dealing with will have forces and position vectors in the XY plane and therefore torques along the Z-axis. Therefore, what I am going to do is I am going to solve this. I'm going to write this in a manner where I don't ever need to invoke the cross product. And for this, I will change the slide for a moment. Please take a screenshot. Please take a screenshot. I will change and I will come back to this. I will change, I will come back to this. But गायब ना हो जाए. So in order to mitigate, in order to get rid of the third dimension, what we will do is we will talk about something which is called the sense of rotation. We have used this when we were dealing with omega and alpha. Sense of rotation. Right now, if you use your right hand thumb rule and if you curl your fingers looking from above clockwise, if you curl your fingers looking from above anti-clockwise, then the direction of thumb will go in two different ways. So if looking from above, if you go clockwise, then the thumb goes into the plane. And looking from above, if you go anti-clockwise, then the thumb goes out of the plane. Right? So what we do is we say that clockwise rotation, okay, is analogous to minus k cap. So see, I'm doing a very clever thing here. I am replacing a legitimate direction minus k cap with a phrase clockwise rotation. And anti-clockwise will be analog of k cap. Now you may choose this as opposite. You may choose opposite. Just like applying right hand control. Yes, yes, yes. Exactly. Yes. So what I'm going to do is I'm going to come back to this diagram. And I'm going to say, wait a minute. This is R1. This is F1. And if I want to take the cross product of these two guys, I've drawn a replica of R1 vector here. Please don't confuse with the vector R1 and the R1 that I have written. R1 in yellow that I have written is a completely different object. It is the length of the perpendicular from the origin to the extended force vector. Whereas the R1 that I'm talking about right now, the black arrow that I'm designating as the R1 vector is the position vector of the point of application of the force from my chosen origin. So if this is the vector R1, and if I apply the right hand rule to find the direction of torque, then the torque will go into the plane of the ball. And this again, if you have not seen this notation before, I will just write it down quickly here. So this means into the plane. This means out of the plane. Right? Basically, you can imagine this is an arrow. The arrow is going away from you. You see the feathers at the back of the arrow, and if the arrow is coming towards you, then you see the tip of the arrow. So the torque must be in this direction. I'm not going to do that. This is too complicated. It's too complicated. What I am going to do, okay, please see carefully. Class may this is much easier to explain. Here it may not be. What I am going to do is I am going to keep my pen on the head of the F1 arrow. And I am going to turn it like so towards the chosen origin. Now you cannot say कि नहीं नहीं मैं तो उल्टा ऐसे इसको turn करूँगा. No, it is through the shortest. So I'm going to keep a pen at the head of F1, and I'm going to turn. I'm just going to draw a line towards the origin, draw a curve towards the origin. And then I'll ask whether this curve is clockwise or anti-clockwise. I'll do it again. Put my pen on the top of the black arrow, head of the black arrow. Slightly twist it towards the origin. Does this go clockwise or does it go anti-clockwise? Does it go clockwise or does it go anti-clockwise? आया समझ में मैंने क्या किया? Keep the tip of your pen on the head of the arrow, the head of the force arrow. Turn it towards the origin. Just draw a line towards the origin. And you will find that it goes either clockwise or anti-clockwise. If it goes clockwise, then that is where your torque is. That is where your torque is. Yeah, it is clockwise. Yes, it is clockwise. The other way to imagine is that forget about F3, F4. And if you have this rigid body like I have drawn, and if you sort of nail it to the wall through the red dot, and you know, if you apply this F1 force, तो ये कैसे घूमेगा? Clockwise घूमेगा या anti-clockwise घूमेगा? Very easy to visualize. It will go clockwise. That is where the torque is. The torque is into the plane of the paper. But I'm not going to use the phrase into the plane of the paper. I am just going to use clockwise. That is the thing. That is the key of handling three-dimensional objects as one-dimensional objects. F3 पे टिप पे पेन रखते हैं और अब क्या होएगा? तब जाएगा ऐसे anti-clockwise. F4 पे टिप पे पेन रखते हैं towards the origin, किधर जाएगा? Clockwise. This is clockwise, this is anti-clockwise, and this is clockwise. I will draw the arrows as well. And now you can choose. Once you've done this, now you can choose whether you want to take clockwise as positive or anti-clockwise as positive. If you choose clockwise as positive, then obviously anti-clockwise becomes negative. If you choose clockwise as negative, then anti-clockwise becomes positive. However, you have to keep in mind that irrespective of your choice of plus or minus, the actual torque arrow for a clockwise rotation, for a clockwise torque is into the plane. Anti-clockwise torque is out of the plane. But you can always say, "Nahi, out of the plane, I will not say it is positive z-axis, I will say it is negative z-axis." Just like in gravity, we could say that नीचे का direction positive and ऊपर का direction negative. So after making that choice, then you can complete step 6. And if I say that clockwise is positive, anti-clockwise is negative, then the torque that we are dealing with is plus, minus,
What are you doing?
oh yeah, सबको समझ में. I hope this is sort of understood. Steps on drawing the rotational free body diagram. Please take a screenshot here. We'll continue from this point. We will, in the next class, see how to apply this, that to find the torque on an object, and then we are going to equate that torque obviously to something. Okay. Any questions, any doubts on this? Good. Chalo, I'll see you guys in the next class. एग्जाम हो गया कि अभी एग्जाम बचा है स्कूल वाला?
हो गया सर.
सर
हो
हो
गया
गया.
ना? चलो.